Hi, my name is Jeff Newell, Technical Service Manager at Ortoped. Today I'd like to talk about a new material called ProComp, carbon-infused technology. Polypropylene has been the material of choice in the fabrication of lower extremity orthosis since the late 1960s. Currently, a new proprietary material that utilizes discontinuous carbon fibers as discrete layers within the body of polypropylene sheet has entered into the O&P market. The carbon-infused polypropylene sheet offers an upgrade in stiffness and resistance to clinical creep. ProComp is the new material of choice by practitioners for thermoplastic clinical devices. The program outlined today will be starting with polypropylene, infusion technical description, ProComp, ProComp thermoforming guidelines, and clinical applications. So let's start with polypropylene, where it came from, chemical origin. Here's a linear schematic showing all plastics are derived from crude oil, then to naphtha, and so on. When the price of crude oil increases, so does the price of plastic. Most of the plastics that we use are based on a carbon-carbon bond. Propylene is turned into polypropylene by linking molecules together. Let's look at the development of thermoplastics in the industrial segment. In 1933, polyethylene was evolved. In 1939, nylon was invented. Interesting story, nylon was invented by Dr. Crothers, who at the time was working for DuPont. He was traveling back and forth from one plant to another in London and New York. Thus came the name nylon. From there, 1941 Teflon, in 1947 48 extruder, in 1953 high-density polyethylene, 1954 polypropylene, 1956 polycarbonate, and in 1959 Lexan. The inventor of polypropylene was Julian Natta. In 1954, Professor Natta developed the ability to polymerize polypropylene into a semi-crystalline material, in essence turning polypropylene into a solid at room temperature. Prior to his work, polypropylene was just used as an adhesive. The first industrial vacuum forming equipment appeared at the National Plastics Exposition in Philadelphia in 1952. Let's move on to the extrusion of sheet polypropylene. Here's a shot of a polypropylene production plant. You can see how massive they are. The extrusion process begins when the bead from plastic is fed into a hopper. The hopper feeds the plastic beads into a screw mechanism. Under the shear and pressure forces from the screw and external heating of the screw barrel, the plastic enters the melt phase. At the end of the barrel, there is a wide die that squeezes the plastic into a wide flat shape. Here's a more detailed view of the extruder. The plastic ends up going through the coat hanger die at the end of the extrusion process. Here are pictures of an extrusion line. The bottom shot is the coat hanger die. Above is the screw barrel. Off to the right, the plastic is being deposited on the highly polished stainless steel rollers. Something to always keep in mind is extrusion-induced material shrinkage. This is something we can all attest to. In the sheets that we receive from production, we always have an orientation differential for polypropylene, copoly, and polyethylenes. The highest bias will be, of course, in the direction that the sheet was made, the machine direction. This is the direction the sheet comes off the extruder. You can see here, transverse direction is 1 to 3%, and machine direction is 6 to 12%. This is a chart showing typical thermoplastic shrinkage of materials we usually use on a regular basis. As you can see, polypropylene is second from the bottom. Polypropylene shrinkage, normal shrinkage is 1.2 to 12.2%. and 1.8% most oftenly used. This pie chart shows that sheets from polypropylene use is very small percentage at 2% of the industrial market. So needless to say, the demand for the O&P market is very small. Too small for FDA classification or control, too small for large proprietary resin formula. What infusion technology offers, custom manufacturing for O&P, specifically designed for the O&P market, quality and batch control, continuing process improvement based on the O&P customer input. The manufacturer is willing to work with the customer and hear the good and the bad. So why the universal use of polypropylene in the O&P field? Let's look from a historical perspective. The best recording of the early attempts of thermoplasting is in the article by Bennett Wilson on vacuum forming of plastics in prosthetics and orthotics. There were a number of groups initially working independently on the process. All apparently were influenced by Dr. Gordon Yates, who first described the use of polypropylene and ABS in the forming process. Dr. Vernon Mooney and Roy Nelson at Rancho Los Amigos were the first to successfully create clear polycarbonate check sockets and then extend the experience into production of polycarbonate AFOs and KFOs. So why polypropylene in the O&P field? Polypropylene has some very good qualities as listed in this slide. For instance, good optical properties, excellent chemical resistance, excellent impact stiffness and balance, excellent fatigue resistance, inexpensive. The list goes on. But there are some negative qualities as well. Some of the drawbacks with polypropylene: thermoforming issues, poor sag strength at a semi-crystalline state, quick viscosity transition at melt state, shrinkage, which is always a big concern, spreading on trim cutout, curling it with foam liners, cold sensitivity, high glass transition temperature. Let's look at ProComp in more detail. ProComp is the combination of two materials, polypropylene and carbon fiber. The polypropylene is food-grade virgin resin, which has less additives, increased thermal comfort, less chance of allergic reaction. The carbon fiber is discontinuous segments, 3/4 of an inch average in length, and flows with resin during the molding process. Here we can see multi-directional carbon fiber infused between two layers of polypropylene. There is a total of 5 layers, 3 polypropylene, 2 carbon, with no exposure of the carbon. No surface penetration, so there's no skin irritation, which you usually would find with carbon. Encapsulated fibers, no toxic fumes during the fabrication process. Carbon is dispersed in a 3D matrix. The carbon fiber flows throughout the molding process, as shown here. The strength of ProComp is one of the key benefits to this material. On the mechanical end, there are also a full range of specifications available. Unfortunately, we do not usually base the design of our clinical products on mechanical factors. Consequently, we usually are not provided with a full set of specifications for the materials that we use. Hopefully, we will have more of an engineering approach for the applications of particular materials in the future. Flexural modulus is a common test used to determine the stiffness of plastics. Flexural modulus, defined as material's ability to resist deformation under load. Flexural modulus is used as a gauge to compare the relative bending stiffness of various plastics. As you can see here, the flexural modulus is 190,000 for polypropylene, which is a fairly good stiffness. Whereas with ProComp, the flexural modulus is 254,000. ProComp is 25% stiffer than polypropylene. Let's continue looking at the benefits of infused polypropylene. Heating. All ovens are compatible with ProComp. Infrared oven, convection, conduction. The molding process. Vacuum, SPE standards, improved sag strength. Finishing, the same as polypropylene. Process parameters respect them all. 10 to 14.7 psi and 430 CFM airflow, and the oven temperature should be at 380 to 390 Fahrenheit. We also have a flow rating for the air. It is not unlike the specifications that we use on pneumatic tools. If you are using a pneumatic cast saw in your lab, you probably have a compressed air system that can deliver a certain amount of air pressure at a specific flow. A vacuum molding system is the same. So we need to have a minimum flow of air. The specifications is 430 cubic feet per minute. So the system requires, from an O&P vacuum system, is 10 to 14 psi with 430 CFM. As I mentioned earlier, heating compatible with all O&P ovens: infrared oven, convection oven, and conduction oven. The molding process compatible with all current vacuum systems, vacuum, SPE standards, also improves sag strength. Finishing, the same as polypropylene. Standing cutting tools as you normally would use, nothing changes. Same cutting tools as you'd use with polypropylene. A variety of grinding tools can be used for finishing the edges, whatever you feel most comfortable with. Here are some examples shown. Flame polishing is also another suitable method for finishing the edges that works very well. As you can see, the edges finish very nicely smooth with no exposed fibers. Transfer paper is compatible. The finish will just be slightly darker. Here are some examples where ProComp can be used. KAFO, ground reaction AFOs. ProComp has no problem where conforming intimately is a must. To conclude, polypropylene is good, but infused version is better. ProComp specifically designed for the O&P market. Thermoforming guidelines use good manufacturing principles. Clinical application. There is no limit to your imagination. Just to look quickly at some further variations. Bubble forming over a prosthetic model using 1/2 inch thickness. Using 1/4 inch thickness. Drape forming over a prosthetic model. Thank you. If there's any questions, do not hesitate to give me a call at 905-869-6037. Thank you.